Condensed matter physics is a branch of physics that deals with the physical properties of condensed phases of matter. Condensed matter physicists seek to understand the behavior of these phases by using physical laws. In particular, these include the laws of quantum mechanics, electromagnetism and statistical mechanics. The most familiar condensed phases are solids and liquids, while more exotic condensed phases include the superconducting phase exhibited by certain materials at low temperature, the ferromagnetic and antiferromagnetic phases of spins on atomic lattices, and the Bose-Einstein condensate found in cold atomic systems. The study of condensed matter physics involves measuring various material properties via experimental probes along with using techniques of theoretical physics to develop mathematical models that help in understanding physical behavior. The diversity of systems and phenomena available for study makes condensed matter physics the most active field of contemporary physics. 1/3 of all American physicists identify themselves as condensed matter physicists, and the division of condensed matter physics is the largest division at the American Physical Society. The field overlaps with chemistry, materials science, and nanotechnology, and relates closely to atomic physics and biophysics. Theoretical condensed matter physics shares important concepts and techniques with theoretical particle and nuclear physics. A variety of topics in physics such as crystallography, metallurgy, elasticity, magnetism, etc., were treated as distinct areas, until the 1940s when they were grouped together as solid-state physics. Around the 1960s, the study of physical properties of liquids was added to this list, forming the basis for the new, related specialty of condensed matter physics. According to physicist Phil Anderson, the term was coined by him and Volker Heine when they changed the name of their group at the Cavendish Laboratories, Cambridge, from solid-state theory to theory of condensed matter in 1967, as they felt it did not exclude their interests in the study of liquids, nuclear matter and so on. Although Anderson and Heine helped popularize the name of condensed matter, it had been present in Europe for some years, most prominently in the form of a journal published in English, French, and German by Springer Verlag titled Physics of Condensed Matter, which was launched in 1963. The funding environment and Cold War politics of the 1960s and 1970s were also factors that lead some physicists to prefer the name of condensed matter physics, which emphasized the commonality of scientific problems encountered by physicists working on solids, liquids, plasmas, and other complex matter, over solid-state physics, which was often associated with the industrial applications of metals and semiconductors. The Bell Telephone Laboratories was one of the first institutes to conduct a research program in condensed matter physics. References to condensed state can be traced to earlier sources. For example, in the introduction to his 1947 Kinetic Theory of Liquids book, Yakov Frenkel proposed that the kinetic theory of liquids must accordingly be developed as a generalization and extension of the kinetic theory of solid bodies. As a matter of fact, it would be more correct to unify them under the title of condensed bodies. History. Classical physics. One of the first studies of condensed states of matter was by English chemist Humphrey Davy. In the first decades of the 19th century, Davy observed that of the 40 chemical elements known at the time, 26 had metallic properties such as luster, ductility and high electrical and thermal conductivity. This indicated that the atoms in Dalton's atomic theory were not indivisible as Dalton claimed, but had inner structure. Davy further claimed that elements that were then believed to be gases, such as nitrogen and hydrogen, could be liquefied under the right conditions and would then behave as metals. In 1823, Michael Faraday, then an assistant in Davy's lab, successfully liquefied chlorine and went on to liquefy all known gaseous elements. with the exception of nitrogen, hydrogen and oxygen. Shortly after, in 1869, Irish chemist Thomas Andrews studied the phase transition from a liquid to a gas and coined the term critical point to describe the condition where a gas and a liquid were indistinguishable as phases. And Dutch physicist Johannes van der Waals supplied the theoretical framework which allowed the prediction of critical behavior based on measurements at much higher temperatures. By 1908, James Dewar and H. Camerlingonis were successfully able to liquefy hydrogen and then newly discovered helium, respectively. Paul Drude in 1900 proposed the first theoretical model for a classical electron moving through a metallic solid. Drude's model described properties of metals in terms of a gas of free electrons, and was the first microscopic model to explain empirical observations such as the Wiedemann-Franz law. However, despite the success of Drude's free electron model, it had one notable problem, in that it was unable to correctly explain the electronic contribution to the specific heat of metals, as well as the temperature dependence of resistivity at low temperatures. In 1911, 3 years after helium was first liquefied, Onnes working at University of Leiden discovered superconductivity in mercury, when he observed the electrical resistivity of mercury to vanish at temperatures below a certain value. The phenomenon completely surprised the best theoretical physicists of the time, and it remained unexplained for several decades. Albert Einstein, in 1922, said regarding contemporary theories of superconductivity that, with our far-reaching ignorance of the quantum mechanics of composite systems, we are very far from being able to compose a theory out of these vague ideas. Advent of quantum mechanics. Drude's classical model was augmented by Felix Bloch, Arnold Sommerfeld, and independently by Wolfgang Pauli, who used quantum mechanics to describe the motion of a quantum electron in a periodic lattice. In particular, Sommerfeld's theory accounted for the Fermi-Dirac statistics satisfied by electrons and was better able to explain the heat capacity and resistivity. The structure of crystalline solids was studied by Max von Laue and Paul Knipping when they observed the X-ray diffraction pattern of crystals, and concluded that crystals get their structure from periodic lattices of atoms. The mathematics of crystal structures developed by August Bravais, Yevgraf Fyodorov and others was used to classify crystals by their symmetry group, and tables of crystal structures were the basis for the series International Tables of Crystallography, first published in 1935. Band structure calculations was first used in 1930 to predict the properties of new materials, and in 1947 John Bardeen, Walter Brattain and William Shockley developed the first semiconductor-based transistor, heralding a revolution in electronics. In 1879, Edwin Herbert Hall, working at the Johns Hopkins University, discovered the development of a voltage across conductors transverse to an electric current in the conductor and magnetic field perpendicular to the current. This phenomenon, arising due to the nature of charge carriers in the conductor, came to be known as the Hall effect, but it was not properly explained at the time, since the electron was experimentally discovered 18 years later. After the advent of quantum mechanics, Lev Landau in 1930 predicted the quantization of the Hall conductance for electrons confined to 2 dimensions. Magnetism as a property of matter has been known since prehistoric times. However, the first modern studies of magnetism only started with the development of electrodynamics by Faraday, Maxwell and others in the 19th century, which included the classification of materials as ferromagnetic, paramagnetic and diamagnetic based on their response to magnetization. Pierre Curie studied the dependence of magnetization on temperature and discovered the Curie point phase transition in ferromagnetic materials. In 1906, Pierre Weiss introduced the concept of magnetic domains to explain the main properties of ferromagnets. The first attempt at a microscopic description of magnetism was by Wilhelm Lenz and Ernst Ising through the Ising model that described magnetic materials as consisting of a periodic lattice of spins that collectively acquired magnetization. The Ising model was solved exactly to show that spontaneous magnetization cannot occur in one dimension but is possible in higher dimensional lattices. Further research such as bi-block on spin waves and NeAQTL on antiferromagnetism led to the development of new magnetic materials with applications to magnetic storage devices. Modern many-body physics, the Sommerfeld-Modell and spin models for ferromagnetism illustrated the successful application of quantum mechanics to condensed matter problems in the 1930s. However, there still were several unsolved problems, most notably the description of superconductivity and the Kondo effect. After World War II, several ideas from quantum field theory were applied to condensed matter problems. These included recognition of collective modes of excitation of solids and the important notion of a quasi-particle. Russian physicist Lev Landau used the idea for the Fermi liquid theory, wherein low-energy properties of interacting fermion systems were given in terms of what are now known as Landau quasi-particles. Landau also developed a mean field theory for continuous phase transitions, which described ordered phases as spontaneous breakdown of symmetry. The theory also introduced the notion of an order parameter to distinguish between ordered phases. Eventually in 1965, John Bardeen, Leon Cooper and John Schrieffer developed the so-called Bcs Theory of Superconductivity, based on the discovery that arbitrarily small attraction between two electrons can give rise to a bound state called a Cooper pair. The study of phase transition and the critical behavior of observables, known as critical phenomena, was a major field of interest in the 1960s. Leo Kadanoff, Benjamin Widom and Michael Fisher developed the ideas of critical exponents and scaling. These ideas were unified by Kenneth Wilson in 1972, under the formalism of the renormalization group in the context of quantum field theory. The quantum Hall effect was discovered by Klaus von Klitzing in 1980 when he observed the Hall conductivity to be integer multiples of a fundamental constant. The effect was observed to be independent of parameters such as the system size and impurities, and in 1981, theorist Robert Laughlin proposed a theory describing the integer states in terms of a topological invariant called the Chern number. Shortly after, in 1982, Horst Stormer and Daniel Tsui observed the fractional quantum Hall effect, where the conductivity was now a rational multiple of a constant. Laughlin, in 1983, realized that this was a consequence of quasi-particle interaction in the Hall states and formulated a variational solution, known as the Laughlin wave function. The study of topological properties of the fractional Hall effect remains an active field of research. In 1987, Carl Muller and Johannes Bednorz discovered the first high-temperature superconductor, a material which was superconducting at temperatures as high as 50 Kelvin. It was realized that the high-temperature superconductors are examples of strongly correlated materials where the electron-electron interactions play an important role. A satisfactory theoretical description of high-temperature superconductors is still not known, and the field of strongly correlated materials continues to be an active research topic. In 2009, David Field and researchers at Aarhus University discovered spontaneous electric fields when creating prosaic films of various gases. This has more recently expanded to form the research area of spontelectrics. In 2012, several groups released preprints which suggest that samarium hexaboride has the properties of a topological insulator in accordance with their earlier theoretical predictions. Since samarium hexaboride is an established Kondo insulator, i.e., a strongly correlated electron material, the existence of a topological surface state in this material would lead to a topological insulator with strong electronic correlations. Theoretical condensed matter physics involves the use of theoretical models to understand properties of states of matter. These include models to study the electronic properties of solids, such as the Drude model, the band structure and the density functional theory. Theoretical models have also been developed to study the physics of phase transitions, such as the Ginzburg-Landau theory, critical exponents and the use of mathematical techniques of quantum fields theory and the renormalization group. Modern theoretical studies involve the use of numerical computation of electronic structure and mathematical tools to understand phenomena such as high-temperature superconductivity, topological phases and gauge symmetries. Emergence. Theoretical understanding of condensed matter physics is closely related to the notion of emergence, where ring complex assemblies of particles behave in ways dramatically different from their individual constituents. For example, a range of phenomena related to high-temperature superconductivity are not well understood, although the microscopic physics of individual electrons and lattices is well known. Similarly, models of condensed matter systems have been studied where collective excitations behave like photons and electrons, thereby describing electromagnetism as an emergent phenomenon. Emergent properties can also occur at the interface between materials. One example is the lanthanum aluminate strontium titanate interface, where two non-magnetic insulators are joined to create conductivity, superconductivity, and ferromagnetism. Electronic theory of solids. The metallic state has historically been an important building block for studying properties of solids. The first theoretical description of metals was given by Paul Drude in 1900 with the Drude model, which explained electrical and thermal properties by describing a metal as an ideal gas of then newly discovered electrons. This classical model was then improved by Arnold Sommerfeld, who incorporated the Fermi-Dirac statistics of electrons and was able to explain the anomalous behavior of the specific heat of metals in the Wiedemann-Franz law. In 1913, X-ray diffraction experiments revealed that metals possess periodic lattice structure. In 1928, Swiss physicist Felix Bloch provided a wave function solution to the Schrödinger equation with a periodic potential, called the Bloch wave, calculating electronic properties of metals by solving the many-body wave function is often computationally hard, and hence, approximation techniques are necessary to obtain meaningful predictions. The Thomas Fermi theory, developed in the 1920s, was used to estimate electronic energy levels by treating the local electron density as a variational parameter. Later in the 1930s, Douglas Hartree, Vladimir Fock and John Slater developed the so-called Hartree-Fock wave function as an improvement over the Thomas Fermi model. The Hartree-Fock method accounted for exchange statistics of single-particle electron wave functions, but not for their Coulomb interaction. Finally, in 1964–65, Walter Kohn, Pierre Hohenberg and Lou Sham proposed the density functional theory, which gave realistic descriptions for bulk and surface properties of metals. The density functional theory has been widely used since the 1970s for band structure calculations of a variety of solids. Symmetry breaking. Certain states of matter exhibit symmetry breaking, where the relevant laws of physics possess some symmetry that is broken. A common example is crystalline solids, which break continuous translational symmetry. Other examples include magnetized ferromagnets, which break rotational symmetry, and more exotic states such as the ground state of a Bcs superconductor, that breaks U-rotational symmetry. Goldstone's theorem in quantum field theory states that in a system with broken continuous symmetry, there may exist excitations with arbitrarily low energy, called the Goldstone bosons. For example, in crystalline solids, these correspond to phonons, which are quantized versions of lattice vibrations. Phase transition. The study of critical phenomena and phase transitions is an important part of modern condensed matter physics. Phase transition refers to the change of phase of a system, which is brought about by change in an external parameter such as temperature. In particular, quantum phase transitions refer to transitions where the temperature is set to zero, and the phases of the system refer to distinct ground states of the Hamiltonian. Systems undergoing phase transition display critical behavior, wherein several of their properties such as correlation length, specific heat and susceptibility diverge. Continuous phase transitions are described by the Ginzburg-Landau theory, which works in the so-called mean field approximation. However, several important phase transitions, such as the Mott-insulator superfluid transition, are known that do not follow the Ginzburg-Landau paradigm. The study of phase transitions in strongly correlated systems is an active area of research.